Welcome back, everybody. Can everybody hear me well? So I just wanted to give you some few messages before we begin. So one of the messages is that the Shu Yu's office hour, which is on Thursdays, she wanted to shift this to Friday this week to 10 to 11. And the Zoom link is still the same as before. And the reason is that she has to present a poster for graduate students. So I hope that's okay with everybody. We share the best. Else, if we look at the topic for the rest of the week and also for next week, we are mainly going to look at theory, which will be linked with the midterm. We're going to use Friday as usual for solving the exercises. In this case, it's the midterm. Feel free to hang around after 4 o'clock. Same with today. If you want to hang around and discuss the midterm, I mean, I have this office hour after the lecture, and there's nobody coming after us, so please feel free. And then also next Wednesday, we are going to just work on the midterm, and the same with next Friday. So we should have enough time to discuss about the midterm. I hope everybody's doing well, even if today even the weather is not good enough either. So thanks for coming again. And what I wanted to do now is to continue the topic we started with last week, which deals with harmonic oscillations. And harmonic oscillations is something you're going to encounter again and again when you study physics, whether you study physics or if you're doing geophysics. It's something you will see being simulated in models for earthquakes. It's a very popular way to simulate earthquakes. Actually, when you construct houses which are meant to resist an earthquake, you often use this kind of modeling where you have a kind of spring between the floors, so the house can oscillate sideways, laterally, and vertically. And this is often the kind of basic model which is used. If you think of the mufflers of a car, we can actually, when we are coming a little bit later, when we start looking at damping, this is a basic model for the way you would model the damping of the car. So I'd wished I had that, because I am a guy which runs my road bike. And when I run on gravel roads, there's often a washboard. And then you go like this on the washboard. And there's no damping on my road bike. So damping is a very important aspect. And you will also see that the equations which we are going to develop, these are equations which you will see again in many, many other fields, as I mentioned, with earthquake modeling, but also when you come to electromagnetism. So probably most of you have taken 184 last year, and then you studied things like different circuits, like an RLC with a capacitance, an inductance, and a resistance. That's a circuit which you can model in the same way as we are going to model now harmonic oscillations. The differential equation you end up with is basically the same. So this is something which plays a very, very important role in physics, but not only in physics. You will find it in many, many different disciplines. So harmonic oscillations, things which repeat themselves in a periodic way, which means that we can often model them in terms of cosine and sine waves. So it's also a very interesting and fun topic. It's easy to model it. You will see that with the forces which we are going to develop, with the accelerations, with and without damping, whether you apply an external force to the system, this is something which you can plug in very easily in an analytical calculation. And for many of these equations, you can solve them analytically, or you can very easily just use a code which you have developed and then solve it numerically. So talking about codes, on Monday, we looked at different ways to solve differential equations. And we have essentially 3 methods which are being used widely. And this is, the first one is the Euler method, which is very simple, but does not conserve energy. And you're going to see that in the midterm, that if you just make a small change using this so-called Euler-Kromer method, where you just reuse the new updated velocity in the equation for the new position, you will get an equation which, or a solver, which actually conserves energy. And for the midterm, this becomes important because you're going to have a force, and I'm anticipating the result in the midterm, you're going to have a force which conserves energy. And you're going to see that. Actually, it's a one-dimensional force, which means that there is no curl. So the calculation should be pretty easy then. I hope you don't get offended. I try to tune it down a little bit due to the circumstances. So, but let's see how things evolve. And remember again that we try to be flexible with the deadlines as well. So that in case things happen and so on, there is always flexibility here. Any questions so far about practicalities and things about the midterm? I don't know if you had time to look at it. We're going to dive into it on Friday. So what I wanted to give you first now is a quick review on how we actually derive the force for harmonic oscillator. And this was based on arguments last week where we looked at the minimum of the potential around a specific point, and then we performed a Taylor expansion. And then we just kept the first three terms in the Taylor expansion, and that's used to actually derive the standard spring force. And this is from where we start today. So let me just bring this up, which we actually went through last week. And then we are going to switch over to the whiteboard rather quickly. But let me remind you of what we did last week. So if you look at the material which we have here, and if we just scroll down a little bit, what we did was simply to perform a Taylor expansion around the minimum of the potential energy. And at the minimum, the derivative is equal to 0, which means that the second term, which you see here, the one which depends on the first derivative, is 0 at the minimum. And then the potential, we assume the potential has a constant value when we put this x variable equal to b. So that means that we can always scale away a constant. If you think of the total energy of a system, that can be infinitely large, but we're always looking after energy scales. So we would typically always subtract away a constant and then refer all the energies to that specific scale or that specific constant. So it means that the first term is something which we often scale away. And that means that what we are left with around the minimum is actually what you see in this equation 2 here, where you now can approximate the potential. If we leave out the higher order terms, we can then approximate that one with a second derivative, which we in turn approximate with a constant. And that is our potential. So that means that we will typically set up an equation where the potential now is given by this constant term, V of B, which we can scale away. And actually just a constant, which means that when we take the derivative with respect to x, this term disappears. And then we are simply left with this minus k times x minus b. And often we would scale the point b to be equal to 0. And that means we just have minus k times x. And that is something which we derived last week. And you see this type of potential is based on an expansion around the minimum. So we are just looking at small oscillations around the minimum. So clearly this expression is valid around the minimum, but it has shaped models like the harmonic oscillator, which is widely used in physics. When you guys are going to study quantum mechanics, you're going to meet the harmonic oscillator because that's one of the cases where you can solve Schrödinger's equation analytically. And physics is very much dominated when you're looking at situations, physics cases at close to the minimum potential is often dominated by this kind of harmonic oscillations back and forth. So it's a very useful model for also realistic physics cases. Now, what we are going to do now is to solve the differential equations. So this is a case where we actually can solve the differential equation analytically. And that means that when we look at the code we will develop in the homework in the midterm, if you take away some of the terms, you will actually have a harmonic oscillator, which you then can solve analytically. And then compare your code with the analytical solution. So let's go through what's coming now is just a set of mathematical steps, and we are going to see that the solution we get conserves energy. And then when we get a little bit familiar with this kind of oscillations, where there is no damping, we are going to add some friction to the equations. And with the friction, we are going to get a motion which is being damped. So it will oscillate back and forth and then come to rest after some time. And this is something for this specific case, which also has analytical solutions. And it's an example case, which you will see in basically all physics courses on mechanics. So let's do that and get through some of the mathematical details. So the rest of the lecture today is actually going to be more about mathematical details and how we solve these equations. So let's switch to the whiteboard and slow down the pace a little bit. Now, guys, feel free to ask questions, as always. For those of you online, you can always place questions in the chat if you prefer that. So what we are going to get now is a differential equation when we now have found this model for the force. So we're going to have an f of x, which is given by a constant minus k times x. And the only assumption we made for finding this force was to assume that we had some small oscillations around the minimum of the potential. And then we just employed a Taylor expansion, and we approximated the second derivative of the potential with a constant, and that's it. So if we do this now and go back to Newton's equation and set up the expression for the mass times the acceleration here, what we have now is this famous equation, which you have seen many, many times. And it's typical when we solve these equations now to isolate the acceleration, which is d of x of dt. And this is given by the constant k divided by m multiplied with x. Now, this constant k divided by m, it's common to rewrite that one in terms of a new constant. And this new constant is actually quite interesting because it's going to define a natural frequency of the system. So let's see those details behind that. So what we will do now is to define a constant omega 0. And I'm going to put this omega 0 because it's defined by the constants of the system, which is given by this spring constant k and the mass of the object, which we are looking at. And this parameter is actually given by the square root of k divided by m. And you can see that this has actually dimension inverse time. So let's take a look at that. So if we take k, the dimension of k here, since k stands in front of x, as we have in the equation here, we know that this must have, since it's a force, it must have a dimension k times x must be equal to mass times length divided by time squared. That means that since we already had length here, we must have that this is equal, this parameter k is equal now to mass. And this is now divided by time squared. That's the dimensionality of this variable k, because we have k times x, and we know that the force is equal to mass times length divided by time squared. That's the dimensionality of force. And we know that acceleration has dimensionality length divided by time squared. So if we now look at this equation here, which we have for omega, is omega 0. If we now put this in, if we look at the dimensionality of omega 0, that is going to be given by the dimensionality of mass, and then it's divided with mass and divided with time squared. So this means that what we have now is something which has a dimensionality of 1 over time. So that's why we call this a frequency, because a frequency is represents something which repeats itself in a certain time period. So that means that frequency has dimension 1 over time. So everything seems to be okay here. And this quantity is often called a natural frequency. So as I mentioned, this example with the mufflers in your car, when you're looking at how to damp properly your car, when you hit one of the many famous Michigan potholes, which I actually did hit with my bike, really bad, and it actually ruined my front wheel. So I am not in a love relation with Michigan potholes. So clearly the mufflers, they will depend on the material you have and obviously the mass. So the mufflers will also have a natural frequency. And we are coming back to that when we are looking at how we can set up damping of, let's say, a specific object. So this is called natural frequency because it's defined by the constants of the system. Now, if we now go back to the differential equation, if we include this omega 0, we are going to get a differential equation which looks like this. So how many of you have seen this type of differential equation before? Anyone's? Yeah, there are quite many. What's the solution to this equation? Anyone who remembers that? This is a famous differential equation in science. And you're going to see, yeah? Perfect. So in this course, we are not going to solve this analytically, but we're simply going to say that the solution is given by a linear combinations of sines and cosines. And the typical way you would prove it in a course like this one is to insert the solution in a differential equation. And when you insert it in a differential equation, you show that this solution actually agrees with the differential equation. But this is a famous differential equation. If somebody gives you that, this is something you should just memorize immediately. This is a linear combinations of cosines and sines. And then I'm going to bring back what we did in homework number 1 with exponentials and cosines and sines. So we can actually rewrite this in terms of exponentials as well. So that's where homework number 1 comes back again in one way or the other one. So let's write down the solution. So the general solution for x, this is a famous differential equation. And if you see that, then omega 0 is a real constant. So that's an important thing. Omega 0 is real. Then the solution x of t, and I'm just writing down the solution, is given by cosine. And then we have this omega 0 times t plus a constant b of sine of omega 0 times t. So if you see something like that, you can just write down immediately the solution. And these constants, a and b, they are defined by the initial conditions of the system. So this is a general solution. And a and b can take any values, which means that you have an infinity of solutions here. However, when you specify the initial conditions, then you nail down the values of a and b. And that's where you have the special solution, which respects the initial conditions. So everything we do in this course is essentially about initial conditions. And sometimes if we venture into partial differential equations, you will also have boundary conditions. And with these ways to initialize and define the system, actually these conditions are the conditions which define the physics of the system. So the differential equation is just a way to rephrase the laws of motion. And then you specify initial and boundary conditions, and then we can solve and find the solution which respects these conditions. So let's now put in a specific initial condition, which I am very fond of because I'm notoriously lazy. So I put always the initial velocity to 0. So we have v0, which is v at time t0. And obviously t0 is going to be set to 0, which is a convenient time. And then we simply say that x0, or x at time t equals 0, is given by some constant x0. So we have initial position and 0 velocity. If we then go back to the equation, we know obviously that if I look at these equations and I plug in the values, if I plug in t0, so x at t0, which is actually x0, that is time a times cosine, and we know that cosine of 0 is 1, plus b, and we know that sine of 0 is equal to 0. So this is 0, no, sorry, this is 0, and this is 1. So this is simply equal to a. And that has to be equal to x0. So that was easy. Now, we couldn't say anything about the constant b. So how can we find the value of the constant b? Because the way we have set up the initial conditions now, we cannot define b, but we can define a. So we have two unknown quantities, which means that we need to have two equations to specify them, right? So how would you go on in order to find the value of the constant b? Any good suggestions? Yeah? Yes, we take the derivative of x because then we have the velocity. And we know the initial velocity, which is equal to 0, and then we can find the constant b. So this is the typical way you would proceed. You have two unknown constants, and then you need two initial conditions. So let's just do that. So I take now the derivative. So we need the constant b. So I take the derivative of d of x of t, and we put t equals 0. And that should be equal to v of t0, which we define to be 0. So this is v0, which is 0. And we know that this is now equal to minus a times omega 0 times sine of omega 0 times 0. And we know that that one is 0. And then we have plus b times omega 0. And omega 0 is different from 0. And then we have cosine of omega 0 times 0. So this quantity is obviously equal to 1, as we know. This quantity here is equal to 0. So that means that we know that v0 is equal to 0. And that is equal to b times omega 0. And we have defined omega 0 to be different from 0 because we have a spring constant, which we assume to be different from 0, because else the force would be 0. And nothing happens, right? That's pretty boring. So we see now that b has to be equal to 0, since omega 0 is not equal to 0. So the only way we can fulfill this is now that b is equal to 0. So that means that we have the final solution, which says that x of t is given by x0, the initial velocity, times cosine of omega 0 times t. So you see now that if you write a code for this system, this should just give us a plain harmonic oscillation back and forth, which then would be defined by the period of the system. So this is a solution which just repeats itself ad infinitum. That means it just continues because there's no damping in the system here. So if you now look at this solution which you have, can any one of you figure out what would be the period of this system? When does this solution start repeating itself? Yeah, exactly. So how would you calculate the period from that equation? Now, if you just think of, so if you just have omega 0 equal to 1, right? When does cosine repeat itself? 2 pi. 2 pi. So what you do now to find the period of the system, you simply say that omega 0 times t is equal to 2 pi. And that's when it starts repeating itself. And you will see this kind of oscillatory motion all the time. So this repeats itself. And this is the periodicity condition. So we can define a period now. So we'll define the period. Let me just put this up here. Which I'm going to call for tau. And this is the time when this just repeats itself of x of t. And in our case, if we now put omega 0 equal to 1, we find immediately that when t is equal to 2 pi, then the solution starts to repeat itself. So that means that in our case, when we have omega 0, so this tau here has to be equal to 2 pi divided by omega 0. So you see now that the period for the oscillation is defined by this natural frequency of the system. So when we have reached that specific value, the solution just keeps repeating itself. So that's pretty easy to set up. So there's one more thing which I wanted to say something about, and that is energy conservation. So let's take a look at that. So if we now look at this specific system which we chose, so we fixed V0, V equal to 0, and then we have an initial position, x of t0, which we simply put equal to x0. So if we now set up the total energy at time t0, which we would typically write as an E0, this is going to be equal to 1/2 mass of the object, kinetic velocity squared, plus the potential energy, which is 1/2 of k of x0 squared. So I'm just plugging in the kinetic and the potential energies. So the potential energy is just given by this k times x squared multiplied with a factor of 1/2, where k is a constant. And what we have then is obviously, since V0 is equal to 0, we have 1/2 of k times x0 squared. And we know that this energy has to be equal, if we want it conserved, it has to be equal to the energy at a given time t, which in our case now would be equal to the velocity at a specific time, v of t squared, plus 1/2 of k of x of t squared. Now, what we know is that the position is given by xt, which is now this x0 times cosine of omega 0 times t. So for the position, we just need to plug in this specific value into the potential energy. And for the velocity, we need to take the derivative of x. And then we just plug that one into the equation for the kinetic energy. So if we now look at the velocity, what we have is that dx of dt is our velocity at a given time. So this is v of t, and that is obviously given by minus omega 0 times x, and this x0 times sine of omega 0 of t. And then I have plus, and actually there's nothing else here because we have only that term, so there is nothing else. And now we can simply plug in these equations. That means that the energy as a function of time here is equal to 1/2, and then I have m, and since I'm squaring this, I'm getting omega 0 squared times x0 squared, and then I have a sine squared of omega 0 t plus 1/2 of k, and then I have x0 squared multiplied with cosine of omega 0 of t, cosine squared. Now, the only thing which I need now is simply to go back and remember my definition of this frequency, which is k divided by n. And you see now that if I plug that one in here, this term here, and I bring it back here, that cancels n. And what I'm left with then is just 1/2 times k times x0 squared. And then I have a cosine of omega 0 t squared plus sine squared of omega 0 t. And I'm not going to offend you guys and ask you what what's inside the parentheses is equal to, but we all know this is equal to 1. It would have been an offense to ask you that, wouldn't it? Okay, so we know, and this is 1/2 k times x0. So what we get then is 1/2 of k times x0 squared. And that is equal to the quantity we define of E0. So energy is conserved here. Okay, so one of the things which we can do next is to look at some manipulations in terms of sines and cosines. But instead of doing that, I want to do something which is a little bit more fun. So I want to take this model which we have, and I want to add some damping to it. And I wanted to show you how we can rewrite these equations in a more general form. And you're going to see that if you go back to what you did in Physics 184, you will actually recognize some of these equations for the equations for a resistance, inductance, and capacitance circuit, an RLC circuit. And that exhibits also harmonic oscillations. So that means that when you scale the equations properly, like we did with the Earth-Sun case, you get a more generic type of equations, which is then similar to many other physics types of equations. So that means that you can have the same differential equations and you could apply them in many, many different physics settings. Actually, this type of equation, which you see here, this equation which gives you the cosines and sines, this is an equation you will encounter when you next semester are starting with quantum mechanics, and you're looking at a particle which is confined to move in a small area, in a box potential. That's going to have the same type of differential equations. And that means that you will have the same type of solutions with cosines and sines. The only thing which will change are the physical parameters. So that's why this thing we started to discuss in the beginning of the semester about scaling equations becomes so important, because then you can actually have a solver which is almost agnostic with respect to the physics. And you can say now, when you have the solution, I just multiply in the right constants. And that's beautiful, because then you have a general solver for many physics equations. So let's, instead of doing this kind of manipulations of sines and cosines, which is perhaps not the most exciting thing, let's now try to add a damping due to the velocity. So we have some kind of resistance or friction term, and then we're going to modify the differential equations a little bit. So let's now look at a more realistic case, because this case here is going to be pretty boring in the sense that it's just going to oscillate back and forth. So it's almost like my voice, pretty boring. And now we're going to add some more interesting physics into. So let's do that. And then we are going to switch over and look at the program and how we can actually program this in a very easy way. So damping, let's bring up that. So what we started with is this equation here, d of x dt, and this is given by minus k times x of t. And this equation here is simply given by a Taylor expansion around the minimum of the potential energy. Nothing but that. And we assume that the second derivative could be approximated with a constant. Let's now assume that there is some kind of damping, and we add a velocity-dependent term. If you think back to the air resistance, or which we looked at in one of the first exercises, we add a velocity-dependent damping term. And the way we're going to do this is simply to add a constant b multiplied with a velocity. So this is simply a new force, b times v. So this is our friction force. So if I look at my differential equation now, what I'm going to get is a differential equation which looks like this. Now, if the velocity is not very large, this is a good model for the damping. If the velocity is large, you may have a velocity damping, which goes like velocity squared. And this contains now k times x. I'm just shifting that to the other side, and this is equal to 0. But you can actually change this if you want to. You can apply an external force to it. So if you think of your pendulum, which goes back and forth, which is also another case of harmonic oscillations, this will come to rest after some time. But you could apply an external force to it. So you can modify this equation by simply applying a specific force. So let's put that in parentheses because that's going to come a little bit later. So we will have this equation here of dt plus b of dt plus k of x. And that could be equal to some kind of external applied force, which depends on time, for instance. So that's a possibility. And we will come back to that. But let's put that external force to 0. We know that the acceleration is obviously given by d of x dt, second derivative. So it means that the first term in that equation is the acceleration. So since we are interested in the acceleration now, and we just remind ourselves that k divided by m is this omega 0 squared. So what I'm going to do now is simply to divide with m over the whole equation. So we divide by m. And then we get a new equation, which goes like d second derivative, which is just the acceleration, plus b times the velocity, dx dt, plus this frequency omega squared, because we have divided out the mass. So we have b divided by m, and this is now multiplied with x, and that's equal to 0. So still, this equation here, there are some constants which we could try to get rid of. So what is common now is to introduce some dimensionless variables. And now I'm going to introduce a new time, which I'm going to call for time hat, which is dimensionless, which is actually given by this frequency times time. So this is a dimensionless quantity because omega 0, has dimension inverse times times time, just gives me something which is dimensionless. And what I could do now is simply to go back to my differential equation, and in everywhere where t appears, I would simply replace with this t hat divided by omega 0. So this is a way to scale your equations. Now, if you think back to the Earth-Sun case, we did actually scale the problem by introducing astronomical units, and we had a time scale which was in years. Because if you want to simulate the solar system, and you want to have seconds as units, you're going to wait forever before your solar system, the code reaches its final time. So when you do the scaling, you introduce a constant which now takes care of the dimensionality, and you have equations which are easier to implement. And you will also see this is not something we do only for the numerics. We do it also when we solve equations analytically. So you will often encounter equations where you scale away some of the constants, because then it's easier to deal with the solutions of the equations. So this is a pretty common way of doing it. And in this case, we introduce a dimensionless time. So that means that when you want back the original time, you just multiply with W0. And then you would have time in seconds or whatever kind of units which you prefer. So if we do that, we get the following equation. I get this W0 in front of this equation, and then I would have a D second derivative. So this is now my dimensionless. It's not a dimensionless acceleration yet, because it depends still on X. So this depends on length, which it should do also. So I get a plus a B times this omega 0 divided by M. And then I have this D of X, and then this D tau hat plus omega 0 times X equal to 0. And I obviously assume that omega 0 is different from 0, because I have a mass and I have a coupling constant K, which are not 0. And now you see that the obvious thing to do now is to divide by omega 0 squared, right? So if I divide with that one, I get rid of it in front of the acceleration. I get rid of it in front of the X term. And then I just get a new constant, which I define in front of the velocity term. So that means that I get an equation now, which is almost ready for numerical simulations. So we divide by omega 0. And then we have a dx, d, this t hat, plus, and I'm going to plug in a new constant, which I will define in just some few moments, but I'm going to call it for gamma. And dx of dt hat plus x equal to 0. And this gamma is by convention given by b divided by the mass divided by omega. And then there's a factor of 2. And this factor of 2 is historical. And I don't remember why. But I think it was a factor of 2, which historically you will see in this type of equations. So this equation now looks much simpler, doesn't it? And when we are going to implement this numerically, we see now that we have an expression for the acceleration that is isolated, and it depends only on this dimensionless time. We have a velocity plus x. So let's now see how we can set it in a specific code here. Because the term which we have here, this term is nothing but the acceleration in terms of this t plus 2 times gamma times the velocity as a function of this t hat plus x times t hat equal to 0. So that means that our acceleration now is simply given by minus x of t hat minus 2 times gamma of v of t hat. So that's the acceleration which we need to plug in our numerical code. Now, when you're looking into the midterm, you're going to have a potential which is slightly different, but you're going to get something which depends on x, but some additional terms. So what I wanted to show you now is actually how you can plug this into the code, which we had from homework 2, 3, and 4. And the only thing you need to do is actually to plug in a different acceleration. And then you can solve the equations. That's pretty nice, isn't it? So let's now do that, because we have the acceleration, and then we can simply set up our good old Euler-Chroma or Euler or whatever kind of differential integrator we want to use. So let's take a look at the Jupyter notebook here now. I was originally planning today to discuss the sinus and cosine manipulations of the equations, but I think this is much more fun because then we can go straight to the physics without too much pain. So let's now look at the, let me just go down. I'm coming back to the mathematical pendulum a little bit later, but we can now look at damped oscillations. So these are the same equations which I put up on the whiteboard. If we now go to the code, we would now have a final time, a time step delta t, as always, we have to define these quantities. This is in one dimension, and we have time, and we have the velocity as a function of time, and position as a function of time, and we now set up the parameter x0, the initial velocity, initial positions, and what I'm going to do now is to put this constant gamma, which you had in a damping form, equal to 0. So let me see if you have a memory which is better than mine. My memory is a goldfish memory, and it needs constant reboots. So if I now take away the damping, what kind of solution do we expect here? What should it look like? Back and forth, right? Pretty exciting. So let's see what happens, eh? Let's see if that fits. So you see now that what I have done is to plug in the acceleration, which we got from this expression, 2 times gamma, and then this x. And then I have, in this case, Euler chroma. So I calculate the new velocity in terms of the acceleration times delta t. I use this new velocity to calculate the new position, update time. And let's see if we get what we should get. Yeah. Let me just shrink it a little bit so we have it in here. So this is pretty exciting, isn't it? So let's bring in a damping here. Let's see what happens, because now we can study different damping cases. So let's take a case where we reduce this or set this parameter gamma. So suppose we put it to 1 here. Now you see something like this. So what is happening here? So we can run a simulation. So next week, we're actually going to look at the analytical solution. You can solve these equations analytically, and then you can actually, so the nice thing here is you can visualize it immediately. You can solve it analytically and extract physics from the analytical solution. But if you now just look at the numerical solution, we put in a damping term. So what is happening here? Any good suggestions? If you were to analyze this when we put in a damping. Yeah? Say it again. Yeah, so gradually it comes to rest, right? So it's being damped. Actually, this has a name in the literature, and it's called underdamping. And that depends on the type of parameters for this damping term which you have. So it's going to oscillate. You see that? So it means that the cosine solution still persists. But now the damping term, it gives it these oscillations. So it means that the cosine term is still surviving, but it comes to rest after some time. So let's try to increase this parameter gamma and just see what happens then. So this is a typical case of damped oscillations. And you see still the cosine term survives here. But let's try to put this value to, let's say, 1.5 and see what happens then. Wow, that was different. So if you look at this behavior, if you think of a mathematical function which expresses this behavior, which function comes to your mind? If somebody gives you a graph like that one, And you were asked, what kind of mathematical function could I use to parameterize those data points which I have? It's exponential. So what you see here, you have an exponential decay. So the exponential decay takes a real parameter. And we are going to see on Monday that the type of solutions which we get depend on the value of this damping factor. So there will be small damping, which means, and that's intuitive, right? Because if you have a small damping, it will keep oscillating, and then it comes to rest. And you saw that in the previous video. In this other case, when we have a strong damping, it just goes straight down to zero. And that is an exponential decay. And that means that the form of the solution is going to be governed by e to the minus something. So we can actually make this kind of reasoning. And this belongs to a domain which is called overdamping, because you have a damping parameter which is larger than a specific or critical value. So clearly, when you are driving on a washboard, like when I ride on a washboard with my bike, I would like to have the soft damping. I wouldn't like to have this kind of critical damping, right? So the way you actually design mufflers is that the mufflers could actually absorb the shock which you have when you hit a pothole or whatever. So next week, on Monday, we are going to look at the analytical derivations. And on Friday, we just keep working on the midterm. And if you wish to hang around, feel free to do that and discuss the midterm. And if you have other things to do, see you on Friday. Good to see you all again. Eh?